So my talk is theory. So there are two aspects of this talk. One is a kind of a general theoretical framework that we are trying to develop, and we have applied it on various cases, and I'll probably give a glimpse of those. But what we'll do is that essentially we are doing orbital or a tight binding model in phase space, not just looking into Warnier state or not just looking into block state, but defining more of a local state in both real and momentum space. And we will try to convince you that that makes this low energy modeling much more easier for both non-interacting case. And then we will take examples for interacting case, especially the mean field case for altermagnetism, and if time permits we will do it for superconductivity as well. And the first part will come from this phase space orbital model for a 2D altermagnetism. It's going to be a prediction in this material, and the second part is done with more paper on a Ising and Raspa spin orbit coupling, and both are being spin singlet pairing in a two-dimensional TMDC. So I'll start with a brief introduction to altermagnetism, and then the essential part of altermagnetism, which is a pretty recent phenomena. We realize that there is a dichotomy between the spin splitting in real and momentum space. And once we sort of look into a thing like that, for us, some of our Middle East people, we realize that it's not something that's the first time we are seeing it. We have seen it in various other ways in the prior literature, and both in experiment and theory. So maybe it's time to look back and see what are the differences and similarities to the earlier literature. And that's what I will do. Then we'll come back to the theoretical aspects of my talk, which is the phase space orbital and mean field model. And then we'll talk about this material. And one of the reasons for the altermagnetism, which we find to be different in this material compared to the other altermagnets, in which there is a spin orbit locking in the interacting quasi-particle spectrum, that's still driven by underlying spin orbit coupling. But here what we find is that it's going to be orbital momentum locking, which will give rise to altermagnetism. And then we'll come back to again the spin orbit driven superconductivity in this material. Alright, so this is the one slide brief introduction to altermagnetism. So it's a dichotomous real and momentum space spin splitting, and essentially it's a merger between the properties of antiferromagnetism and ferromagnetism with sort of a no net magnetization as in antiferromagnetism, whereas there is a momentum space spin splitting as in ferromagnet. And these are roughly the band structure that one would expect, and there are more details about how the spin splitting would be, because we essentially need to have the total magnetic moment to be 0. So there has to be a spin splitting to reverse across the Brillouin zone, and it was predicted pretty recently and then followed by many materials realizations. So I just took few of them. And also there are review articles. I think this is even review article. And the material that we are going to look into is indeed a controversial one. And we, in this process of doing this research, which we wanted to focus on the 2D material, but then we went to the 3D version of it, we did find that there might be resolutions to the controversy. All right, so before I come back to altermagnetism, let me just go back to the literature for about a decade or so, in which I do have my biased literature in which I was part of it, to talk about in various contexts how where this sort of spin dichotomy that we have seen. And one of them is this classic hidden order story of a heavy fermion compound probably from 85, um, from Leiden, and it sort of has been solved and unsolved many times in the literature, including a resurgence of this field around 2010 or 11, where I was doing postdoc. So I was also looking at it, and that reminds me of what it is. So it's a tetragonal lattice with uranium compound. It's a BCT with an antiferromagnet, with one layer being ferromagnet, another one, middle one, is antiferromagnet. And as a function of pressure, at ambient pressure, there is a phase transition. There is a huge entropy loss that we see in thermodynamics and many, including in electronic structure, but there is no really magnetic phase transition. There is no magnetic moment, or maybe very tiny one, and then it goes to an antiferromagnetic phase. And despite the fact that there is no net magnetic moment, but there is a strong spin fluctuations in this material, and in fact it even goes to soft mode at some point, and that led to many proposal, including quadruple moment and all. But interesting part is that even if you look at the band structure, despite having no magnetic moment, but there are spin splitting, and that's roughly what we see in altermagnet as well. So while I was working on this, we came up with a proposal called spin orbit density wave, which in an animated way, that's roughly what it is. You start with a spin split band with these two color representing different spin in different orbital, and then with some Fermi surface nesting, you do have a nesting that comes between different spin orbit bands, and then we open a gap, mean field gap, and what you have is a spin split band but with no magnetic moment. And that's what we call it, spin orbit density wave. And excuse me, in real space, it's like a two interlocked spin density wave in different orbital with no magnetic moment. And in fact, it also doesn't break time reversal symmetry, or that depends on the details. And then we wrote a mean field Hamiltonian with two orbitals with a spin orbit coupling. And then we have some mean field gap, some density wave gap, and with a gap that opens between the two different orbital and two different spin, giving us a quasi-particle band with a spin split quasi-particle bands and no magnetic moment. But around the same time when we were working on it, this is where the topological insulators were also very hot. And we looked into this Hamiltonian and then compared with one of the first paper of 3D topological insulators in 2009, and we see that there is an uncanny similarity between those two models. I will not go into the details, but this is a non-interacting one having two different sublattices and a spin orbit coupling. And you can see that this spin orbit coupling is the spin orbit coupling here between different sublattices, and there is a interlayer hopping that in this case this comes from interactions. So what this means, the underlying spin splitting that we are talking about with giving no net magnetism is also something that was roughly at play for topology. And that sort of observation gave us an idea to engineer topology or to engineer real space spin polarization. So this is completely opposite to what we are going to talk about altermagnet. It's that there is a real space spin polarizations, but no spin splitting in the momentum space. The idea is roughly simple, that we start with some 2D electron gas with a Raspa spin orbit coupling, which will have a spin split band structure, and then with sandwich with another Raspa spin orbit coupling band with opposite spin orbit coupling, and then what we get is a spin orbit degenerate band in the momentum space, whereas there will be spin polarizations in the real space. And then once we turn on coupling between them, we can open a gap and we can even convert this into an insulator, which is the topological insulator. And we did a low energy modeling for the predictions, and we were trying to come up with materials. Then we were talking to Alex Zunger's group around that time. They were also looking into real materials to find this sort of a hidden spin polarizations in centrosymmetric materials. And they came up with this material in which you do see that there are different layers which sort of act as an inversion partner to each other, giving us each layer will have spin orbit coupling spin splitting, whereas the band structure doesn't have the spin splitting. Yet it has a raspa-like spin orbit band splitting. And then followed by many materials, including TMDC and as well as cuprates. There has been many such materials. Okay, so that sort of give us the background of the spin or real and momentum space spin splitting dichotomy. So let me get back to altermagnet. And the material that we are after is ruthenium oxide, and this also has a similar sort of similar crystal structure as uranium ruthenium to silicon 2, except the c-axis lattice constant is probably smaller than the other one, but it does have, however, the center atom has opposite spin polarizations. And if you look at into the band structure, it does have the signature of altermagnet with spin orbit spin splitting being reversed along two different directions. But experiments are divided with some supporting altermagnetism and some opposing it, not being able to prove the spin splitting. So what we did is that we looked into 2D versions of this material, and this is the AB plane in which the ruthenium atoms are here, and these are the oxygens that link them. The phonon is stable, and this is the band structure, giving us the quintessential signatures of spin splitting along the gamma to m directions, which reverses as you go to the other directions in prime. All right, so this is what we are trying to understand, and then we sort of try to explore further that why, or let's say the phase diagram before we even come back to unravel why the experiment has been controversial. So what we did is that we scanned as a function of U and strain for this material, and we did see these are the magnetic moment for ruthenium 1, and this is the magnetic moment of ruthenium 2, with these two color reflecting up and down spin. The third one is a oxygen offset, the distance between this ruthenium to ruthenium or from ruthenium 1 to oxygen along these directions versus this direction. And when it is white, that means there is no offset, and when there is a finite color, that there is an offset, and that offset is the reason where this this antiferromagnetic background becomes altermagnet. And that's probably the reason this material is sometimes showing altermagnetism and sometimes showing not, because of some intrinsic strain which can be very small, or also according to the calculations what sort of U one would choose. And so now we want to understand it with some low energy modeling, and to do that, typically what we do is that we develop a tight banding model or 1 year orbitals, and to do that we see that near the Fermi level these are the orbitals which are present, dxz, dyz and dg square, and dg square is the blue one which is pretty dispersionless and also not much of spin splitting, whereas the dz and dxz and dyz orbitals has the spin splitting. And that gave us that we can actually work with two orbitals here. On the 2D plate, a dg orbital will look like s orbital with less spin splitting, and the dz, dxg and dyz will look like a px and py orbital projected onto the xy plane. So we work with two sublattice and two orbital model, and the orbital we consider is two sublattice means a and b, and we have s orbital, and what we do is that we actually take a linear combination of px py to even go to a minimum model of px py, and this is how they will be oriented on the px py orbital. And then we look into the symmetry. What we find is that so one thing I forgot to mention, so in altermagnetism generally some sort of a non-symmetric symmetry is required to give you a momentum space momentum resolved band spin splitting, and that's what I'm going to explain here. And that's generally a common theme, And here it sort of comes in this way that you have this space group with a translation that is non-symmorphic translation, and it works like this. So suppose you have these two orbital, and under a mirror, which is the symmetry of this point group, your orbitals are flipped from P plus goes to P minus, and P minus goes to P plus, and then with a half translation, then you get back to the same one. And half translation or non-symmorphic symmetry gives you a degeneracy. So this one you can see that it becomes -1 only along some particular k directions, and when operator square becomes -1, that gives you the Cramer's degeneracy. So it acts like a pseudo Cramer's degeneracy or pseudo time reversal symmetry in the system, and this is why you see no spin splitting along some directions and spin splitting along other directions. Okay, and that's the underlying theory about altermagnetism, and it's also orbital momentum blocking. It's the orbital flipping under mirror without looking into the spin orbit coupling. In fact, with the DFT, we showed that with spin orbit coupling, the spin splitting or magnetism phase remains the same. Okay, you probably have 5 to 10 minutes. Or
you have 6 minutes
for the talk.
for the talk.
All right, so let me now develop this tight binding model, which we call phase space orbital model. So it roughly goes this. So suppose we have some momentum space in which we talk about a block state, right? And then if you go to real space, we talk about something like a 1 year state, and one would have a Fourier transformations between them. So what happened is that if you are working with momentum space, everything is extended and you have global properties like topology and all. But once you go to the real space, getting a 1 year orbital, which has to be then local, there is an obstruction. So you actually won't be able to develop tight binding model properly if you want to capture these global properties, and thus vice versa. Okay, if you have some local properties that sometimes don't get captured in momentum space. So that's what we started thinking along some other context about why not doing in the phase space itself. Write the state, write the Hamiltonian is phase space, and then we sort of transform into our any space that we want to see, a spectroscopic signature of such thing. So here it is. So we'll call this block phase in terms of z as a function of k and r, and then so instead of taking a Fourier transformations to go to momentum space, we take this entire thing with the block phase and the 1 year orbital, and you can also add the spin as a product state. And these three components is give us the product state in the phase space. Okay. And then sort of adding anything spin orbit coupling or spin momentum coupling or even orbital momentum coupling, anything that you want to entangle now becomes much easier to do before we do the Fourier transformation or symmetry analysis of anything. Okay. And then we will write the tight binding Hamiltonian, which will be both again in momentum space and real space, in which generally what we have is some sort of a dispersion that captures all these terms together, but here we will keep the block phase and orbitals and spin separately, and we'll do a summation over real space as well as over the momentum space to get to the full Hamiltonian. So doing the summation over the space, the real space or momentum space at the end, not at the state level. That's roughly how it differs from any other existing model. Okay, and so the orbital or spin part, we generally put the symmetry in the usual way, but in the block state one, this is the to look into the symmetry. What you do is that we first look into the nearest neighbor. Here between the T1, T2, T3 and T4, these are the block state. Then we apply the symmetry, then we reduce into all the irreducible representations. So that sort of give us the sense that what all the hopping that are allowed in this system are completely restricted by symmetry, and that's exactly the irreducible representation that will also dictate what sort of order parameter, a magnetic or superconducting order parameter, that will also appear. So all these things will be now defined within the same irreducible representations. And in this particular case, you will have some extended S wave and dxy and PAF and so on and so forth. And then what we do is that we add a mean field Hamiltonian for the altermagnetism here, and then we split it. And here all these indices are probably not so much important. So this is the block phase part with respect to some center of motion. So there will be only one of them that will appear, and then we write in terms of this E reps, and then there will be the sublattice and orbital and spin. So you can see that this one will not have any spin flip, but the altermagnet will have the spin flip, whereas all these things will now be written in terms of the same E reps for both interacting and non-interacting part. And that's the simplification that we achieve by going into this way of writing it. Huh?
Just 2 more.
Yeah, it should be done. So, and what we do is that instead of again doing a tight binding fitting to the non-interacting band, and then we come up with a mean field theory for the interacting part, what we do is that we first write the mean field theory and then do the fitting. So in this way, the magnetic part is also sort of a kind of a fitting parameter to get this, to capture what sort of a altermagnetism and what sort of spin texture one would have. And as that's the case for any orbital symmetry, that 1s orbital doesn't necessarily have the same symmetry as the atomic orbital, what we find is that the magnetic part also do not necessarily have the same symmetry as the DFT would predict. Rather, it has kind of a symmetry that we call it Warnier altermagnetism, the symmetry that sort of reproduces or fit to the low energy part of this spin splitting. So what we find is that there are three components of the magnetism that arises here. One is some sort of some component of ferrimagnetism having some small magnetic moment difference between the two sublattices, and also we find the spin orbit density wave moment that we earlier predicted for hidden order state in uranium ruthenium 2, whereas the dominant term still comes from dxy like symmetry, both intra-sublattice and inter-sublattice components. So those are all the components which are also irreducible representations that do appear in this material. So with that, I think I will rather stop here for only covering the 2D altermagnet part for these ruthenium oxides, showing that there are 2-3 masses. One is here the controversy was because maybe there are some internal strain, or in the DFT case there might be some interaction parameter which we are not taking, or different people are not taking same value, and that's probably, and the altermagnet is very sort of sensitive to those parameters, and the underlying orbital spin locking is causing the altermagnetism in this compound. And we proposed a phase space orbital model, and I was trying to justify that makes things very easy, not only for magnetism, but also we did it for some gauge field, tight binding gauge field model for Kitaev-Hanekom model with a Marana band, and also some Bogoliubov orbitals, and so on and so forth. All right. So with that, I will stop, and thank you very much for your attention.
Okay. And my questions. That's good.
Suppose I take an alter metallic state, increase the volume. So at some point, what will happen when the charge gap opens, in addition to the one electron gap? How will it express from the Heisenberg band?
Yeah, exactly. So I mean that's a kind of a general statement. Maybe the instability will start changing, because here we're only looking into one instability, and also because of some underlying symmetry and all. So, but one thing that makes things different from antiferromagnet to an altermagnet is the non-symmetric symmetry. The sort of a distance along these two directions are different. So and that was created by some strain.
Imagine what city.
But those will be, yeah, I mean, those will be at a higher U limit and all. I mean, they are the physics are going to change and so on. Yeah.
Hi, Pranay. So the phase diagram you showed between the strain and the U, basically. So you are changing the U and also relaxing the system, and the
Yes.
strain is appearing on its own. So in the phase diagram, the strain, which is the reason of altermagnetism and causing the spin split band.
No. Strain here was also a fitting parameter. So that means as we are varying strain, there are pressure in the system.
So the Hubbard U is the reason for the magnetism, and the strain is the reason for this spin splitting and altermagnetism. Once the magnetism is already there.
That is true. For the magnetic instability, that is true, that U would play the role. But to make an antiferromagnet to an altermagnetism, it is the distortions which is taking a proper point group symmetry C4 symmetry to a lower symmetry C2 symmetry, and that was causing the spin splitting.
Thanks.
But that can also naturally emerge.
That can also naturally emerge.
It not arise from strain only.
Yeah. So that was the point. So in the depends on what U value. So even if you look at the phase diagram, even at zero strain, if you have some U value where it is naturally occurring.
And at large value, it will always become a monster.
Very large.
Any other questions? Yeah.
Nice talk. So, sort of a naive question. What you mentioned, TMB is having this momentums in relation. Right? So, there are these sort of theory proposals for using twist as a parameter.
Yes.
Altermagnetism.
Altermagnetism as well as patches of ferro and antiferromagnetism. All sorts of interesting things are there.
So, where do you think that, how should I think about going from this picture to something like that?
I mean, generally speaking, if I think of a twisted bilayer, and in ways because of the local network and nearest neighbors, environments are changing, so there will be exchange coupling which will be inhomogeneous, and that will correspond to magnetism being inhomogeneous in the system. But the point I was making is that the dichotomy between real space and momentum space. In that case, there will be domains of magnetic moment along the real space, but what that would manifest in the momentum space, that would depend on the symmetry. If I don't have any sort of a proper symmetry to protect it, you will probably get a spin splitting, much like a ferromagnetism or whatever. But under certain non-symmetric symmetry, that actually can convert into a altermagnetism.
Moving to the last question. The last one, really last one.
He has the last say.
That strain which you showed, 234, that's an intrinsic strain or external?
So as I was saying, in theory it's a strain, but that doesn't give the ground state. So yeah, at a given value, there will be in some cases that will be an intrinsic one. In some cases, because we are tuning it, right? So when you are tuning it, there is only one value which is the intrinsic. The rest is yeah. There will be only one point which is intrinsic, and the rest of it will be some pressure in the system.
We have had a very large number of questions. Let's thank Tanmay once again.